So good morning. Today we are going to see recurrent neural networks and convolutional neural networks. These are very common type of networks in deep learning in general. For language and text, we depend more on recurrent neural networks, but it is worthwhile to look at convolutional neural networks as well because there are applications that require them. So before we start, I'd like to have a recap of what RNNs are and what we saw last class so that we can move further smoothly. So the first thing is RNNs are used for modeling a sequence. We saw that a sequence has two properties, order and varying length. Both were addressed by RNNs. However, we saw that they suffered from vanishing and exploding gradients because the derivatives had to be multiplied in a recurrence, that is in a iterative fashion. Hence, we saw one very simple solution, which was gradient clipping, which was basically setting a threshold so that the gradients don't explode. So now we're going to see various ways. So we do not use RNNs as they are for text. Even in the tutorial, we had used LSTMs. So we will be seeing LSTMs in detail and other variations of RNNs that have created good space for text modeling. So we saw exploding gradients with gradient clipping. How do we handle vanishing gradients? So you might guess the thing is we don't want it to go near zero. So like we had a threshold for the upper limit, we have a sort of threshold for the lower limit. Now to address that, we can have a gate. A gate can restrict both it going higher and lower, which means that I will allow only a certain amount of information to pass through my hidden state. So what do gates do? They optionally let information through. They have a neural net layer. Again, whenever you have the sigmoid layer, it's for differentiability, it's for combining things, and it squashes, it's called like a squashing function. So it squashes between values. Just having a recap of things we have seen so far in this course. They are also able to remove or add information to the cell state. Now I'll explain with an example later on. So there are three gates in LSTM. They call input, output, and forget. These gates protect and control the cell state. So what does this mean? We had a very simple hidden hidden state node sort of concept in RNNs. Here, your simple hidden node has become a bit expanded. It has an input gate, an output gate, and a forget gate. These gates monitor how much information is there. That is, what is your hidden state derivative value in some sense, and make sure they're within acceptable limits. So once again, you have the previous input because you need to model sequence, and you pass it to the output, and you have outputs passing through the cell state. Now, in RNNs, you had only a hidden state kind of network. Here you also have something called a cell state because it's a bit bigger. So this is a diagrammatic representation. So you have your usual recurrence, which is xt minus 1, xt, xt plus 1. Here ht minus 1 is used for basically output. So ht minus 1, ht plus 1. And this would have been our hidden state in RNN. Here we have this entire cell, and these are the gates. These are gates which we'll be seeing in detail. How they restrict the information, what are we going to do with it? So first, it transports information through the units, and this is CT minus 1 to CT. So we know that we have a connection between the hidden states so that we can maintain the sequence. We know the order. So the connection between the hidden states again is for order information. Now the horizontal line that's running across the top mentions that. We'll be adding things, subtracting things, controlling things So those are the functions of the gate. So the forget gate decides, as the name suggests, what information to forget or throw away. How do we do this? What we do is very simply, we take a fraction of that information. How do we take a fraction? Again, we use sigmoid because sigmoid is between 0 and 1. So we take a fraction and it is a function of the previous hidden state and the current input. So once we have these two things, we squash it into a fraction. And you have to remember, it's important that these parameters or coefficients for the sigmoid are going to be learned in this process. So you do have, in a way, a more complex model. And when you have more complex model, you need more data to train it because these parameters are going to be trained as well. Now you look at ht minus 1 xt, output a number between 0 and 1. So this is your forget gate. So what it does is, if I keep 1, that means I pass the entire information into the gate. Now, if everything was 1, it has the potential of leading us to an exploding gradient. If it is 0, it will become, 0 when you multiply, it will become 0, there's no problem. But if it's just slightly more than 0, then it can lead to a vanishing gradient. So this controls the amount of information and it's known as a forget gate. The next one is an input gate. So not only are we controlling the amount of information from the previous state and the current state, here we are focusing only on the current state. So sigmoid xt ht minus 1, and then we have a tan h also. So this is like, tan h is how the hidden cell state would have been calculated. So here we are having a function of the current hidden state basically. So your current hidden state is a function of xt and ht minus 1, again maintaining the order information, and this is your input, which is xt and ht minus 1. So what this does is that we are going to see how much of the new information to bring in. Once again, the sigmoid ensures it's a fraction. So already we have two layers of complexity, the forget gate and the input gate. And this is a function of the cell state. So the sigmoid layer, called the input gate layer, decides which values we'll update, and the tan h layer creates a set of values that can be added to the state. So to sum it up, because this is getting a lot of values, so the first one was just a simple fraction, and the second one is a function of the cell state itself. So you have an extra tan h. So this is known as the cell update function. So here we have a sum. Already in the forget gate, we had a multiplication, which was multiplying the previous cell state. After that, so that's our ft into ct minus 1 plus it into c tilde t. So this is now our current cell state. Finally, we will have our output gate. So we are again controlling how much information is going to go out over here. So that, again, we take sigmoid of whatever we are predicting and we pass it on outside. So in this way, we are controlling input, output, and how much we should pass across the cells. So with these controls and the fact that these parameters are learned during training using backpropagation and propagation through time, we are making sure that the problem of exploding and vanishing gradients is not there. Because here, even though the weights are tied, Even though you have the same weights across the cells, the each cell has its own forget input and output gate that are controlling the amount of information that needs to be passed on across the states from the input and to the output. Next, we have another variation which is called as the gated recurrent unit. So that was all about LSTMs. To recap, we had three gates to control information, and that solved the exploding and vanishing gradient problem, provided it is trained on a large data set, because we saw if the sigmoid becomes 1 or very close to 0, we'll again have the same problem. So gated recurrent unit is a simpler version of the LSTM actually. There are two gates, update gate and reset gate. So this means there is basically one of the gates is missing. I am not able to make out which one from the LSTM. So yeah, when we see the thing, I'll understand. So update gate, it determines how much of the past information needs to be passed along to the future, which is our cell state update. And so again, we use the sigmoid. And the reset gate depends on how much to forget. So I guess the output gate is not there. One of the gates is not there in the gated recurrent unit. And so it is a slightly simpler model to train. So if you have less data, instead of going for LSTMs, you can go for gated recurrent unit. So because this controls how much information you have, how much information you pass on, how much to forget, etc. That is why these networks are called memory networks, because they sort of remember some part of the past. By remembering, it just means that uh, some information has not left the cell. There is no way to access that information or memory or anything like that. It's just a way of saying that we have passed on only a fraction. So there is so if I pass on say 80% of the information, 20% is technically within the cell. That's what you think logically. But of course, as programmers, you know that if you have computed point 0.8 of something, you cannot access the point 0.2 of something. It's not stored anywhere. So when you see these terms called memory networks, you should not be under the impression that you are storing information in the cell. It's basically how you process the data. That is what matters here. And there is nothing like you are holding information in the cell and saving things in the cell. It is a normal neural net kind of architecture. It's just how it's interpreted. So let's just quickly see LSTMs as a GRU. And in LSTM, because of the output gate, we are making sure that we access only less, not less, like a controlled version of the memory. Whereas GRU exposes its entire content. We don't have output gate. It performs quite well because, as I told you, it has the advantage of having less parameters. You don't have to learn the parameters of theta. And it depends from task to task, but both are quite competitive, and depending on the problem you have, the data you have, you can go for either of them. So these are the two main ways of handling this exploding and vanishing gradients. Now we are going to see slight variations of RNN so that you are aware that these are architectures that are available, and you'll be able to apply it basically. Now tree NN or recursive RNN is very interesting because it addresses a fundamental structural problem in computer science, which is that our neural networks are not interpretable, or they are not mapping functions of text as such. So we have embeddings which are very useful, but which have nice properties, but we have not addressed the property of compositionality. In the sense, if I use this sentence, the country of my birth, then the vectorial representations of the sentence should compute to another sentence, to another vector which represents the sentence. Once again, I should be able to deconstruct and get the final sentence as well. So in an RNN, I would just have the country of my birth, and that would have some input embeddings, and then I'll pass it on to my hidden state. In a recurrent NN, I do it in a hierarchical fashion so that there's a sense of compositionality. And this brings out nice interpretations, like the meaning of the sentence is determined by meaning of its words and the rules that combine them. So this makes it a stronger version of the representation. So you basically, it's again, if they're all sigmoid nodes only, you keep passing it on, and you have learnable parameters and tied weights. It's the same as RNN, but you have extra connections and in a hierarchical fashion. Now, this leads to many interesting things. You have sort of phrase similarities. You have so in this can be something a good competitor to doc to it. But you can't use full documents because hierarchical functions, you can imagine this will explode a lot. So it's better for phrase which are smaller. And you can also do it for like pictures in a hierarchical fashion. And this idea is what is going to lead us to convolutional neural networks, which we'll be seeing next. Another interesting thing is the multitask RNN and the deep RNN. Deep RNN is basically when you take a lot of LSTMs and stack them on top of each other so that you have a much stronger representation. Once again, all these things about stronger, more complex models I'm saying, they are only useful if you have more data so that you can learn the parameters of these complex models. Ideally, we would love a simple model where I can run large data on it as well. That would generalize much more. For example, in one of the tasks that I'm doing right now in my postdoc, I was given a data set with 1,000,000 features but only 100 samples. What the algorithm would do is just, it will take the first 100 samples and just sort of mug that up because it will not generalize. It will just take that as the feature. So when you test it, it is going to come almost nearly zero because to update weights, so if I had just 10 features and 100 samples, after 10 samples, if it had mugged up the first 10, in the 11th sample, it will be forced to make a change on its parameters. So all these things about complex, it's not that necessarily complex models are better, but we need to know what is the entire set of architectures you can have in your arsenal and apply them accordingly. Another interesting thing is multitask RNN architecture, which is you use um, the same network to do various NLP tasks. So you can have NER over here, and you can also do, part of speech tagging, so on and so forth. So what happens is for the various tasks, so this is basically person, this part is the NER, this is a sort of language model which gets the next word. So since these tasks are tied, you get richer information and you also get better ways of representing things because your hidden state layers, your RNN layers are going to encode much more information because your error is based on two tasks here. So this is NER, which is named entity recognition, and here it's recognizing this person as a person. PER, so it's PER, O, and O. And here it is getting the next word, and here it's getting the previous word. So this creates a very strong binding and makes sure that we move forward and get a richer representation in the hidden state. Okay, I'm going to start convolutional neural networks. So I suggest we take like a 5 minute break and then we can go ahead. You can ask if you have any questions till now. Okay, so now we'll see convolutional neural networks. So, as I discussed at the end of RNNs, it is always good to learn a small model. Now, all the networks we saw till now are fully connected networks in the sense from the previous layer to the next layer, all sets of nodes are connected. So the idea of convolutional neural networks is whether we need all these edges while modeling a particular set of data, and whether some of these can be shared so that we have to learn less number of parameters. So the idea is, imagine we had a bird classification task. Now, some of these patterns are much smaller than the whole image. So for example, only this particular portion is going to detect that there is a beak, which is one of the things that are going to identify it is a bird. So let's say this is an animal classification rather than a bird classification. If it's an animal classification task, this would be a kind of differentiating feature. So, but it's only this part of the uh, entire image. And you can also see there's so much of background which is unnecessary to identify if it is a bird. So once again, and then you have claws that are a bit significant for birds. And all these things are very small. Ah, so I will get the whole thing. So this head structure, eye structure, so they occur in different parts of the images. Here it is sort of in the upper left of the image, and here it's sort of the middle image. Now what will happen is that In a normal fully connected neural network, these two would be identified with different weights and different parts of the image. Because, as I said before, just like how text is passed as embeddings and representation in a low level manner, for images, input would be passed as simply RGB values. So the algorithm has no way to detect that these are very similar. All it knows is that in this pixel position there is potential useful information to differentiate that the animal is a bird. And in this portion also there is useful information. But we know that these two are similar and the weights can be shared. So this is the idea of convolutional neural networks, that we leverage this information that is occurring on different parts of your input. So what is convolution? It has a number of filters that does a convolutional operation. So convolution is basically a set of matrix operations that condenses the matrix. So we will be seeing how that happens. So let's say we have two filters which are smaller matrices. So I have a 6 cross 6 image and I have smaller filters of size 3 cross 3. So what this is going to do is it's going to filter this information across this matrix. That is the first step. We decide the filter and then we apply it on the image. So let's take the first filter, which is sort of like the diagonals are positive 1 and remaining is negative. So here, when we apply the filter, we'll take the dot product and we will get 3 because the other values are 0. So you will get the value 3. Now, this is known as a strided convolution. So when your stride is 1, you basically move this window by 1. So it's over here. Now the dot product for this is minus 1 because minus 1 into 1 is minus 1. Minus 1 into 1 is minus 1. So we've got minus 2. And finally 1 into 1 is 1. So minus 2 plus 1, you get minus 1. So now you can imagine as it strides across, you will get a vector of length 4. Now a stride is equal to 2. First you'll get 3, but then the window moves by 2. Now what does this mean? That means first the computation changes, that it is minus 3. So you get minus 1 into minus 1, minus 1, 1 into minus 1, minus 1, and here 1 into minus 1, minus 1. So it's minus 3. Also, your information here or the vector here becomes much smaller because when your stride is 2, you can do only 2 operations, 1 and 2. You cannot move it further than this. The filter can't be cut off. You want the entire filter. So because of that, you'll have only 2 values in your vector. Whereas in stride equal to 1, you would have had 4. Okay. So this is depicting stride equal to 1. And this is for the entire image. We have finished stride equal to 1. So we can check it that, we have our diagonal values are 3 and 3. And this is repeated for the next filter. So far we saw the first filter, which was the 1, 1, 1 on the diagonal. Now this is the second filter and we will repeat it again. This will, hello, is there a question?
Yes.
Yeah.
Yes, ma'am. The stride will be applied only horizontally or will it be applied vertically too?
It's applied horizontally. Yeah. You can code vertically things if you like. The
No.
idea is that anyway so let me go back. Yeah, so the idea is that I'm applying the stride vertically first time. Then the next time I'm going down anyway. So it covers the entire image. Am I
Okay.
clear?
For 2, when the stride is 2, will we go down by 2 or 1 only?
That I'm not sure actually. I have been thinking it is one, but it might be two also. That's something I need to check. I don't know. I've not thought of that.
Okay.
Okay, so I'll continue now. So we apply this for the second filter, and now we have a matrix, two matrices, one for each filter. So this is known as a feature map. So now from your 6 cross 6 image, you have two 4 cross 4 images of sorts, and this forms 2 into 4 into 4 matrix. So this is what is called like a tensor because it's a vector of matrices sort of thing. Sorry, matrix of matrices sort of thing. Now, to add to the complication, you also have in an image the RGB values. So you can add filters for each. You can do the same feature map for the three colors. So that will just multiply this by 3. So you'll totally have 6 of these matrices. So to compare convolution and fully connected network, in a fully connected network, you have a set of inputs that are fully connected with a set of hidden states and then the outputs. Here, it's a sort of compression. You have compressed the image into useful information, into a set of matrices. Now, what are the advantages of this? You have fewer parameters because from if you send this to a fully connected network, your set of inputs is 36, but here it would be 16. Of course, we will be seeing how we will be combining the different filters. Right now, the difference between 32 and 36 doesn't seem big, but you will be seeing that these feature maps scale much slower than the image sizes. But the first thing is there are definitely fewer parameters. The second thing is that uh, the output will be connected only to um, 9 of the inputs. So what I mean by that is that so this 100 sort of gets compressed here and so on and so forth. We'll be seeing a more worked out example, you'll get what I'm saying. And it's also the fact that you can see by the value of the numbers, right? You get 3 minus 1. So it reduces the um, sort of space of values so that you can compute even better. And I forgot to mention an important thing that there are shared weights between these values. So that leads to less parameters. Everywhere you have shared weights, it means that while training these weights, it should not be updated. And that leads to less parameters for learning. So to give an example, we'll have a convolutional layer, a max pooling layer that I'll be showing later on, and this will be repeated multiple times. And now at the end of it, we will have a set of matrices. These set of matrices will be changed into a large matrix and then fed forward to a normal fully connected network. But the idea is that the flattened network will be much smaller, much denser, and much more informative than our original image that we had. So max pooling is very simple. It's just that we take the max of subsets of your matrix. So we had a 4 cross 4 matrix. We'll change it into a 2 cross. We will change it into a 2 cross 2 by taking the max. So we take 3, 0, 3, 1 and minus 1, 1, 0 and 3. Why are we doing this? It's because subsampling in images does not change the object. So when I subsample a bird, by subsampling I mean it sort of In Word, you drag, drop the size, or you change the size of the image. There is the information is exactly the same. And the way this is done, you can see it's sort of reducing the metrics. And that is why it's important the way you do pooling also. So when you do it uniformly like this, it makes sense. If you are going to do max, say across this rectangle, it will not create this very nice resizing of this image. So the structure is also important. So once again, what this will do, we have a smaller matrix, you have fewer parameters. So to recap, what are the advantages of CNN? You reduce the number of connections, you have shared weights, and you use max pooling, which further reduces the complexity. So you had a 6x6 image, and you finally end up with a 2x2 image. Now, this is called a filter. In convolution, we use the term filter. So what this is going to do is you're going to apply this filter like how we saw in the strided convolution and get newer values. So it's just a repetition of what I've said. So you have a new image and then you can keep applying it further and further so that you get more and more compression. So you get a new image here, you get a new image here, and you can flatten it. And you can imagine there has to be a limit because if you keep compressing beyond a point, you're not going to get useful information. Finally, you flatten this into a single vector and then pass it on to a normal fully connected feed-forward network for classification or whatever task you have at hand. Now, all this I was discussing because this still has significant use for text as well, because you have, say, a sentence matrix which is describing a document, and you want to know what are the parts of the document I need to focus on and finally get the output. This is, I guess, in sentiment analysis for the document. So it will do a convolution on the various sentences across the document, and it takes phrases and things like that. Just before we finish, I'd like to talk about two types of CNN. We saw strided CNN where we took a simple dot product. In kernel CNN, you use the same filter, but we multiply it with a kernel function. You might have studied SVMs in your machine learning course, where in kernels we change the dimension or the space in which you are operating because things become much easier to classify in a higher dimension. So that was my discussion on CNN. We'll take a small break. We'll meet at 11:30 for our discussion on sequence. That is a little lighter subject, and we'll discuss the assignment for the course at that time. So thank you.